All right. Hello, everyone. Welcome to this session this afternoon. I'm Vijay Saraswat, operating today as an advisor to Relational AI. You see Relational.
And I'm Nick Vasiloglu, VP of Research ML at RelationalAI.
So thank you so much for joining us. We have a lot of material to cover today, and I hope you will find this material exciting and interesting. In any case, if you have questions, when you have questions, please interrupt us. We sort of know what we are trying to say and the flow. So if we can take your question right then, we will. If it makes more sense to take it later, then we will postpone. Excellent. Let's get started. And this did not work, but this should work. Excellent. So we had promised that this would be a hands-on session, and here is what we mean by hands-on. Your hands on your keyboards. So this is the URL. If you go to that URL, and if you scan this stuff, you should go to a page where there are a bunch of prompts. You can cut and paste from those prompts into your chat session with GPT. We are using GPT-4 as the main engine to drive home our points, and we will tell you why as we go through it. So you should be able to copy and paste and see results similar to what we will show. A few of them we might actually show live here as well. And if you try something that is different, please do. And it's something that you think you want to share with everyone because you got something interesting, or you want to hear our comments and you think you can communicate all of that in your, just telling us what's going on, please do that as well. Unfortunately, we are not set up to share screens, to share your screens. Okay, so let's get started on the real stuff. So I don't know about you guys, but I certainly feel a bit shell-shocked. I have been in this field for 42 years. And this is the first time I will say, in my way of looking at it, this is the biggest thing since the development of Fortran. I'm a programming languages guy. Fortran was a very big deal. Hey, old enough, right? Not old enough to have worked in the pre-Fortran days, but yeah, I have my share of punch cards. And that time, the development of Fortran was something that actually made computing accessible to a much larger set of people than those who could figure out for a particular computer what the zeros and ones meant and program that in assembly. So it was a big step up. And of course, that led to a whole revolution of a large bunch of programming languages, etc. What we are seeing now is a similar but a much more gigantic step. And our way of describing that is the first generation of computers for humans. And by this, what we mean is computers with which humans being non-professional programmers, can interact. And in fact, these computers that they can interact with, these particular, by computers here, I'm talking about today's conversational systems, which have inside them a large language model. I'm talking of those computers as being the first generation of computers for humans. Again, we will take GPT-4 as our exemplar of such a system. So what we now have is a family of instructable computers, instructable because you can actually get these darn things, these language models to do things for you. You can instruct them on certain stuff, which is not what anybody in the field would have anticipated even 5 years ago, that the realm, the whole domain of natural language understanding, the bunch of researchers who work there would actually produce a computer that could take care of a whole bunch of instructions for you. That was not where we thought the field was headed. So it's a big deal that's instructable computers. It's a family because, in fact, as you will see, there are literally a few dozen of these beasts out there, these beasts that look like this, that can be used to do this sort of stuff. And in fact, they have some similar characteristics and some very different characteristics. So we will touch on that a bit. But here is the big deal. They can all read, they can read the language that is accessible to you. In this new world, we have to actually kind of define our words very carefully. I mean by language here, what humans use to communicate with other humans, with other computers. So that includes text, documents, HTML code, because that's what you use for computers. And soon we are promised is going to include also images, audio, pictures, video in one system. Today you see separate systems that do these sorts of things. So soon we should have one model that is multimodal in this way. So it can read all the language accessible to us. We are behind a firewall. We work for a financial institution. We've got private data. There is no issue in the sense of having that private data be made accessible to a language model that lives on the intranet, does not go outside the intranet. So your Chinese firewalls are protected. They protect the access to that information. Understand it, communicate with us and each other somewhat as humans do. Of course, the whole big deal is what the heck does that mean? Somewhat as humans do. We are going to get into this. The main thing I want to point out, because this is a big problem we see today, so many people out there on the evening news, including CEOs of very big companies that have funded huge amounts of stuff here, making significant mistakes about what the heck is going on. So I want to be very careful and not introduce any ideas today about, oh my God, we are on the path to AGI. Not going to use any of that terminology. I'm simply looking to see, do we have engines, do we have computers here that can help us do our work better? And by our, I mean typically professionals at work, people in the finance industry, legal industry, attorneys, medical, healthcare, entertainment, so on and so forth. So that's our intent. What these systems have in common. So the reason that people are getting so excited and thinking about these as new artificial intelligences is because they have a lot of characteristics similar to the characteristics of humans, and I've described them right here. They can deal with language. And until now, the only processing systems, information processing systems we have any familiarity with are biological humans who understand how language operates, who can take instructions from us if they feel so kindly disposed in language and go execute them so that together we can perform some task. What we used to have before are digital computers that you program, you talk to, get them to execute your instructions in a very different way. So it's natural to sort of latch onto, oh, these things are like humans. But the failure modes are quite different. The way they generalize is quite different. So I would urge you, as you go through this presentation, to look at them as just a new kind of computational system that has very interesting characteristics, and critique and understand that in that way, rather than thinking of them as these are new kinds of humans and there's an artificial general intelligence and so on. We have liberally stolen from other people's ideas. This is not intended to be an original contribution at all, this whole presentation. And you will find credits at the bottom left, the slides from where we have stolen the ideas, the papers, and so on. This just came out a couple of days ago, and I thought it was very interesting and worth putting up. What you are seeing now is a whole range of people, writers, artists, Snoop Dogg, I think that's his name, getting on and talking about with obscenity. And listen, I don't know if you guys saw that, this little clip of him saying, that old guy of AI, the godfather of AI on TV, he's saying blah, blah, blah. What does it mean for us in tons of obscenity? Anyway, Kate Crawford is an author, and she put this comment out, which Dan McCreary, talks about in his blog post, which is again clickable here, and that it's a moment in time when, and she's talking about what she works with, it looks like things are changing completely. And I have appropriated that theme to talk about where in the knowledge infrastructure, that's what I care about, knowledge infrastructure of a firm, the infrastructure that supports the processing, the extraction of information from documents, email, all sorts of stuff, chat conversations, Bloomberg chat conversations. I've worked in the financial industry, so a lot of my stuff will be, tainted by that, so to speak. So we have, sources of information, many different sources of information. We have, the knowledge architecture issue is the issue of understanding how we organize on our intranet these various sources of information, how to extract information from them, how to make them available to humans, professionals in the enterprise to work with them. And, we used to have this kind of a thing, if you've got to get stuff on the cloud, you've got to get knowledge graphs, your query languages. Oh, maybe BERT is going to actually make things interesting. And now suddenly we have a right angle a turn here where a whole bunch of new ideas are coming up which look like they will shape a future in a significant way. So this is the elephant in the room, or according to Dream Studio, I told it to put it in a room, and that's where it put it. We have an elephant here that we need to talk about, which is what does the whole knowledge graph enterprise as a foundation for the knowledge architecture of a firm mean in this new age when we got some very powerful language processing capabilities available coming at us, so to speak, from left field? All right. So that's our agenda. We're going to talk about the following things. How did we get here? And then working with unstructured data, that sort of seems like the sweet spot of these technologies, but we will show you that in fact, you can also work in very interesting ways with structured data using large language models. We'll talk a bit about the tradecraft. How do you make these things do more interesting things for you? And then ultimately our view of how these things become the knowledge hub in the modern information-rich enterprise. Again, I'll take the usual examples: financial firms, legal firms, accounting firms. In fact, entertainment industry, movie making. There's a whole bunch of discussions going on right now around how all of that changes. And of course, medical and health science as well. Here is a way that I used to think about things. I gave a talk at Park when GPT-3 came out, because I was very, very impressed with GPT-3 2020 early and what it was doing. And the ideas of an advice taker come from John McCarthy very much early on in the 60s, at the time that the whole thing, the idea of AI as a discipline came about. And in some sense, again, these are our personal biases. You may disagree. If you want to raise a disagreement right now for us to deal with, we can do that. Otherwise, I'm happy to take it afterwards. And oh, Blake, I forgot. Blake actually was also going to tell all of you folks that there is a reception after this that people are invited to.
Yeah, I'll tell you. I should say.
It's a happy hour that's happening right after this in the Anything at All restaurant right there.
Awesome. So people are invited to that. So in any case, it was, in my view, the tremendous amount of work that a whole bunch of AI scientists did from the 56 onwards counted for moving this clock from the viewpoint of, have we progressed on the advice taker idea? The advice taker idea is, it's a system that you as a human talk to and give some advice about the task that you want to accomplish, and the advice taker assimilates those things and goes and gets tasks done in the real world. McCarthy's view of AI is a system that helps get tasks accomplished in the real world. And that's an operational definition that we will take for the kinds of systems you're after. So my take is that, in all the years till then, till about 2020, we kind of progressed on this doomsday clock, start at noon, end at midnight, the AI clock. We sort of, and what do I mean? Well, what will midnight correspond to? Midnight corresponds to, I have an advice taker. I have a system that can take in all the information that I, as a professional, am processing, perform these tasks in a significant way, or help me get them done in a significant way. Again, I don't want to talk about AGI. And in that context, I would say, these are very qualitative judgments. We had advanced to something like 3 minutes after noon. Huge runway to go. And I thought after GPT-3, maybe we're 5 or 10 minutes after. It's a big jump up. Now we're at GPT-4. It's a much more powerful system than GPT-3 or ChatGPT, if you're used to ChatGPT. And it looks like, whoa, there's a pretty big leap here. We're at something like 3 p.m. There's still 9 hours to go, still a long ways to go, but huge jump in just 2 or 3 years. So let's get into this. What the heck is going on? How did we get here? So I assume most of you are very familiar with the basics, so I'm going to jump over this very, very quickly. The idea is to lay this in a context where we can understand. I've spent most of my life working in systems, computer science research, and in AI. So for me, and programming languages, we did the extend language here. So for me, the whole sort of computer science 1.0 was the work that said, hey, you want to accomplish certain tasks, you the human, you the programmer, need to go understand which real-world phenomena, real-world tasks, which real-world phenomena you need to model in your system, inside a computer, using floats, strings, other data structures built up on top of that, Canonical example, you want to transfer money from somebody's bank account to another. Well, okay, you got to have the abstractions of, here's my account, there's my account, I need a transaction, needs to work canonically, so on and so forth. Somebody needs to figure out the algorithms. Somebody needs to write the code for those algorithms in an appropriate programming language, and so on. So when you know how you're going to accomplish a certain task, well, okay, there's a pathway. Well understood, big tower here for how to get things done in the old-fashioned but extremely powerful way. Most of the computing systems that we are using today are actually built like that. The big virtue of this is you can sort of get exactly what you ask for. Maybe at a big price, maybe it takes a lot of humans, a lot of time to do it, but you know what you are going to get. And I think the bridge between this 1.0 and the new 2.0 system that I'm going to talk to you about is through this business of sketching that Armando Solar-Lezama and Ras Bodik and a bunch of guys developed maybe about 15 to 20 years ago, with the idea that actually the programs that we are writing need not be complete specification of the algorithm. They could have a fair bit of blocks that are left open. And the system figures out how to fill those blocks in order to get this program to run without exceptions and taking advantage of other artifacts that you would give to the system, not just your half-filled code, but also things like, oh, here are a few examples that it needs to run correctly on. Here's the input, here's the output. Here's some types for the holes that we are leaving behind, some other auxiliary pieces of information about how to complete the program. That, in some sense, in a very large way, is what we get to with CS 2.0. Molam wanted to make the point that, look, 1.0, 2.0 doesn't mean that we have gotten rid of 1.0. It just means, in my way of talking about it, that this is a significant change from the way we were doing things before. And going forward, I fully expect, in fact, all our work is about how to use 1.0 ideas, most of our work, 1.0 ideas on top of 2.0 ideas. So what is this? This is where you get to when you don't know how to write the code. So the normal way of thinking about it, you don't know how to write the code, let's pack up and go home. There's nothing left to do. But no, let's imagine you actually have a huge amount of data available to you. That's the missing link. So here's a canonical example. You've got pictures, images like this. The task is to label those images with pieces of text. People, child, house, study, and so on. And as you can imagine, large images taken from anywhere in the world, huge sample space, and your task is to write one function that's going to analyze any one of the samples presented from this large space and be able to label it accurately. Again, you may not get 100% accuracy. You're looking for as well as you can. So you're already in the realm of you're going to have to deal with noisy, uncertain, high-dimensional data. Here you might have like 1,000 times 1,000 pixels each with 3 bits associated with them, and so on and so forth. So noisy, uncertain, high-dimensional data. We got that. Let us imagine we have a fair bit of it. Now, the question is, what does fair bit? So let us just look at the first example where these things really were made to work, and that's the Feifei Li's work on getting about 60,000 examples done of how you label these things. And so you have 60,000 examples of input images labeled with these pieces of text. And now the goal is, if you just have that, can you actually somehow magically get the code for this agent, for this program that takes as input an image and produces a label? Of course, it will take as input an image that it has never seen before. That's the interesting bit. If it just memorizes the 16,000 produces label, what good use is that? So can we synthesize the code for this agent? Again, similar to the sketching thing that I talked about before. And if we take this as our exemplar question, the question now becomes, what is the mathematical framework? What is the new computer science that lets us do that? And now we get to neural networks. We get to stuff that Jeff Hinton, Jan LeCun, Benjio were working on from the 80s onwards. It's taken about 35 years of a lot of hard work there for us to get to the stage now where these things are giving us the performance that we are seeing. So what do you have? You have this idea that you don't have the code, but let us imagine that we have moved to continuous functions. That will turn out to be an enormously powerful assumption to make. And so we are looking at approximate functions for those agents that we talked about. So what are we going to have to do? We're going to have to look at a space where those functions are expressible in a parametrized fashion, meaning you've got a function. That function that you saw before has maybe 1,000 parameters. How about 1,000,000? How about 1,000,000,000,000 parameters? So this approach is going to allow us to scale up to the known, today it's known more or less that GPT-4 is based on a large neural network with 1,000,000,000,000 parameters. So what you have is a space of functions where each instance has a certain value for this 1,000,000,000 parameters. And the whole game is to figure out the values for those parameters in such a way that for your input and output labels given to you in the 60,000 data set, they work beautifully. And of course, what you needed to do is to learn how to generalize, meaning on example inputs that are very different from the ones you have seen, but drawn from, as the statisticians like to call it, the same distribution, you should still get meaningful answers. Very tall task. And of course, the thing that you want to do is to ensure yourself, to ensure that the system family of functions that you're working with needs to satisfy some kind of a universality property. The big insight that the pioneers of this space had going back a long time is that these so-called distributed representations. Why are they distributed? Because what we have, our computing elements, our neurons, are actually utterly simple from the viewpoint of computer science and the amazing programming language constructs that we have in functional logic, constraint programming. These things do something utterly simple. They will take input from a bunch of prior such elements and combine them with the weights, take some multipliers, take some additive combination of these things, and then apply a nonlinearity. Nonlinearity is something quite simple. Let's say you got a function, and the function's value here, I'm giving you the so-called ReLU function. The input is negative. We want the output to be 0. The output is positive. We want that to be tracked by this nonlinearity. So we apply that nonlinearity on this. We produce stuff. You keep doing this. That's all that is going on in this entire system. Of course, it is assuming that you started out with your input as vectors of some floats, potentially largish vectors. In the case of text, today we're talking about 768 long vectors for each token. So a tremendous amount of input is coming in and processed in this uniform way. And the output, as we will see soon, is actually going to be text. So text that is represented in the same sort of 768 long vectors in the output, and then you simply do a transcription of that output to get actually the text. The system internally is working all on vectors in these high dimensional spaces, and those turn out to be a very nice mathematical base to take for this sort of computation. The big deal here is the deep stuff. And the deep stuff arises from the following intuition. Again, going back to this example of labeling images. Here, let's just talk about labeling faces. We will have images coming in here. You want so-called feature recognizers that are able to say, this is all taken from this Benjo tutorial, these guys tutorial 2015, that say there are edges here. And then you want the next layer to build on the abstractions learned by the first layer to say, oh, there are combinations of edges here, ultimately leading up to a higher layer where you can actually see in the representation that that layer is working with ghostly images corresponding to that input stuff. And now you can imagine a layer on top that is saying, oh, let us classify it in one way or the other. It's a cat, a dog, and so on and so forth. And ultimately, this all relies on a big hypothesis, which is the so-called manifold learning hypothesis, which is that the data in this world is not random. Randomness is huge. It allows the number of random strings are, if you look at just natural language, absolutely immense compared to the number of strings that are meaningfully carrying information for others. And so the idea here is that the things that are carrying information actually lie on this special kind of a mathematical structure called a manifold. And so if we learn that manifold from our data, we will have a much easier task of performing a large number of tasks on top of that learned representation. This whole thing is about what I described earlier in the 1.0, I have to produce my own abstractions of bank accounts and so on. Forget all that. The whole game here is from the data, the system will learn the abstractions that it has to work with in order to achieve the objectives of its learning operation. The objectives are typically, you get the output, you have a label. The label may not be the same as the output when you're training. So then you take a loss, you take a difference between these, and you propagate that. I'll talk about that in a second. You propagate that down, and so on and so forth. So the idea is that the data that's of interest to us actually has a special structure. It lies on this manifold. And so we are in a position where we need a relatively small amount of task-specific data to get this to do really well on that task. And most importantly, if you do this right, then the same underlying learned manifold will help us take care of a whole bunch of tasks. This is the sort of stuff we are now seeing come to fruition with large language models. Please.
I'm just curious about the weights. They're probabilities based on what?
Good. So we'll come to that in just 2 slides. Okay. So what do we need? So this is exactly the central issue. Where do these weights come from? So obviously we're going to learn these weights using some algorithm. And that algorithm is stochastic gradient descent. Again, I just think of it in a very simple way. You got this loss function. You're looking to minimize that loss function. We may, many of you may have done this in high school algebra. You were given, say, some convex function like this quadratic curve, and you had to find the minimum. And the way you do it is you find a point on that curve. You look at that point for the direction of steepest gradient descent, and you're taking the tangent here. You move a small step in that direction, you repeat. You're essentially going to follow this curve down to a minimum. When that gradient starts increasing, you've reached it, you can stop. Utterly simple intuition. Here I'm talking about, just a 2-dimensional variable. Now let's imagine doing this in a space where there are 1 trillion parameters, not just 2. Turns out the same basic idea works, and it took a long time to make it work. There's no intuitive reason to believe that this thing is going to work. When you don't have convex curves, when you are working with non-convex problems, and in fact, there's no guarantee that there's a unique global minimum. It took a whole bunch of things working together, and I've got a bunch of papers here for you guys to look at if you're interested, to actually reach the stage where people were able to train parameters first with millions of train models with millions of parameters and actually find their way through without gradients exploding or gradients vanishing. Then learning will stop, find their way through to a minimum. The whole bunch of things here I see already have taken up a lot of time, so I'm going to skip over this. So the short answer is this. You start with a network, let us say for the sake of simplicity, randomly, the parameters are randomly initialized. And then we're going to run this algorithm. And this algorithm you can think of, there's a very simple intuitive explanation for this problem. You think of it like this. You provide some input, it's got some output. That output may be different from the label that you got. Okay. Now look at the derivative. Look at, for some parameter inside, twiddle its value slightly. Increase it or decrease it. It's a floating point number, so you're allowed to do those operations. Now look at what happens to the label. What happens to the output? Does that increase in the direction that you want it to increase, closer to the label or not? If it does, excellent. You want to keep this. You do this simultaneously for 1 trillion parameters. That's the magic of stochastic, and there's a bunch of stochasticity involved. Stochastic gradient descent. That's the intuitive idea. Of course, as I said, there's a huge amount of craft here and technology that makes all of this work. Okay, this is where I will stop this introductory part. It's the bitter lesson. There's one thing I'd like you guys to go afterwards and read to understand profoundly what is going on today. It's this blog by Rich Sutton, a famous researcher in reinforcement learning, which explains where is it that we were going wrong. So I was at Xerox PARC in the late 80s, early 90s. I was doing AI, the good old way, symbolic AI, building up models of photographic copiers, of copiers with discrete control in them. You got to model the paper path, these things continuously moving. Fantastic, great challenge. I loved it. What was I doing? I was trying to solve the problem in my head, like a whole bunch of people doing symbolic computing at that point. You do that, Rich's point is you're doing the wrong thing. None of the breakthroughs in AI, and again, Debbie's here, so I don't really want to be slaying too big an emphasis on this, but let us, if she's not going to interrupt me, then I think maybe let me just quickly get off this slide and finish it. The point is, his point is that the bitter lesson is this has never worked in terms of making progress in AI. Humans, smart humans, spending the time figuring out what the problem is, how to solve it, figuring out the algorithm, coding up that algorithm. As soon as you deal with noisy, uncertain, high-dimensional, real-world data, we are just not in a position. We have seen empirically that our work simply does not get us those breakthroughs. His point is that it is when we start building systems that can actually learn from data at scale. And by scale, I want you to keep this in mind, 1 trillion parameters. That's the scale we are talking about. When you're able to reduce a problem into a context where you can learn from data, there are 1 trillion parameters, then a whole new regime emerges where you can build these systems that actually do great stuff for you. So these are the 3 quotes that I have extracted from here that to me capture the essence of how machine learning based modern techniques are actually changing the world. So now we're going to shift gears. What I talked about is general machine learning stuff. It doesn't really speak specifically to language, but the rest of our presentation today is going to be about natural language and the advances that have been made thereby. And I think of it as something like this. We found a wormhole to accomplishing a lot of tasks in the real world, my working definition, McCarthy's working definition of AI. And we found that by simply working in this new paradigm with some very clever ideas that I'll get to in 1 second. Before doing that, let me give concrete evidence for what Rich Sutton was talking about. Tons of us, and I was doing some of this work 30 years ago, tons of us were in this business of figuring out how we can understand text, natural language understanding. And the way you do it is you build a parser. You build a complicated parser on top of which is able to take care of all the complex all the complex language phenomena, long-range dependencies, anaphora, so on and so forth. People who did lexical functional grammars, a Stanford Park, joint project over many years. There are literally hundreds of computational linguists who have poured their energy and soul over decades into this enterprise. We never, and again, my friends there will disagree with me, I think, so I'm giving you more of my bias. I'm giving this bias from the viewpoint of the NL practitioner, not the viewpoint of the theory guy who wants to understand every detail of semantic phenomena in language, which is where most of these folks derive their inspiration. But my point is we never got to a point where we could release in the wild a system that understood text in the way that these modern systems are doing. So I consider this essentially obsolete because this tide of statistical learning and deep learning representations and frameworks takes care of that. Okay, this is the technology in one slide that at some level, you should have some passing familiarity with these ideas to understand what is going on. First and foremost is, I gave you a generic introduction, a very quick introduction to neural networks. It turns out that how you organize those neurons, what kind of layers, how they interact with each other is utterly important. That's the architecture. And there is a big problem when you deal with language. Language is sequential in nature. So we are going to take a piece of text, we've got a token, a piece of word at the very beginning, a piece of word at the very end, they're going to interact with each other. The usual ways that we had the so-called LSTMs and RNNs of dealing with this before the transfer came about were simply not good enough to give us a coherent account by training in this way of these long-range dependencies. So this was a major innovation just in 2017 to intuitively go to this point where instead of threading the interaction between the first token and the remaining token, the last token, through a finite state machine, through a state which held the current view of everything that has been seen so far, and at each step you compute possibly an output or you compute the updated state, you thread it all the way to the end, the mediation between the first token, the last token actually goes through the state. Simply does not work when you want to be able to understand large pieces of text and so on. Usual problems, tons of stuff, won't go into it. The transformer architecture point is simply that instead of doing this linearly, let's put the input tokens and the output tokens on a vertical and a horizontal axis, and every pairwise point of interaction there, we will have some learnable weights, and this is the self-attention architecture, and we will of course do this in levels. So the level idea, what you saw before in the vision space, you build up progressively more complex patterns. That's a big deal here in natural language as well. Ultimately, these systems are learning really complicated patterns in natural language. So we need a loss function. We need something to know whether this stuff is learning something that is relevant to language or not. And the big problem here is we want to do this intuition, and we discussed it already, that scale matters. And so scale matters. So we need to be able to deal with massive amounts of text as our input. It's not going to work to have the Stanford graduate students label that text. There just aren't enough of them, much as we would like otherwise. And so you need a way to do what is called self-supervision, which is essentially from the raw text, just language as it occurs in the wild, web pages, books, articles, whatsoever. We need a way of constructing a loss function. And this is the central idea of the language model. Let's take as our objective predicting the probability distribution over the next tokens. That's what a language model does. Give it any piece of text, it will give you, if it's a good language model, it'll give you a realistic prediction of the next token that is to follow this previous stuff. Now, of course, once it does that, you can repeat the problem. You give it a new input, which is the previous input plus this token, have it again predict the next thing, do a beam search. Now you can get extensions of this text. So from text, you can produce text if you have a great language model built into your system. And this language model is what we are going to train with this massive amount of text. The point is we can train it because when we get this piece of text from our input data that is not labeled, just text, we can simply take away this last token. We know what the token is, we take it away, we feed the system this whole thing with a blank for that token, ask it to predict that token, and it'll predict something, we got our token, take the loss, we are great. We are now in a space where we can iterate using stochastic gradient descent, this as many times as we need over as much data as we need, the system will learn something. This I should point out upfront. In the 1.0 way, we were able to design precise systems that actually did work for you exactly as you intended them. You are not going to get that here. When this whole effort started and you were training on this massive amount of text, what system you would get out, what properties it would have, it's very hard to predict ahead of time. It was the intuition of some researchers that we will get interesting stuff, and absolutely we got interesting stuff. And this is another big point that goes in. Before this, I described that you have a task, labeling an image. For the task, you got a neural network. You're going to learn how to solve that task by doing all of this training. But we have thousands, tens of thousands of tasks. We're not going to go create a separate neural network for all of them. This idea enables you to say, don't worry about it. Here's what we're going to do. We're going to learn a single network, and we're going to take all our problems that we got. If we can, we're going to represent them like this. A piece of text as input, a piece of text as output. You want to summarize a passage? Excellent. Give it, here is the passage, please summarize it. That's your input. We use the power of language to describe all of these tasks that might be of interest to us. Not everything is describable in this way. Some are. Do that, and presto, if we are able to train this system in such a way that can solve all of these tasks, then we got that single engine which will take care of summarization, take care of sentiment labeling, take care of translating from one language to the other, take care of extracting information from a document, and so on. And then the other magic we've already discussed is scale. Started out with GPT-3 small, 125 million parameters, all the way up to 1 trillion parameters now. Increase the size of the stuff you're dealing with, and finally, you've got a scalable engine that is able to learn these complicated patterns. But there's one last thing to say before we get off the slide, and that is, it turns out this is not enough to actually get to instructable computers. Computers that when we interact with them and we tell them, here is our task, we need to summarize, we need to translate, and so on, they will actually stay on task. We want to be able to get to a place where we say, here's my task, do it. It does something. We look at the output. We say, this wasn't right. And we say, please fix it. And we give it some feedback. And it goes back and fixes it. All of this stuff is around dialogue management. Well, at least it tries to fix it. It's around dialogue management. It's trying to get it to stay within certain guardrails. To do that, there is another idea which uses reinforcement learning in a very interesting way, called reinforcement learning with human feedback. This was the critical step in 3.5 over 3.0 and for GPT-4. I'm talking about GPT. GPT-4 also has a significant portion of this. The downside is you've got to engage humans to look at outputs from the model, two pieces of output, two possible continuations, and say which one they prefer. The great thing in doing it in this way is you don't have to ask them which is the right answer. They don't have to solve the problem of, is it the right answer? They just have to solve the problem of which one is better in terms of accomplishing the overall task versus the other, express that preference. When you do these human sorts of things, it's a hard task to get all humans to agree on what the task is and do things consistently. And so being able to simplify the task to say, hey, we are just going to express preferences has turned out to be a scalable way of doing this. A whole ton.
The answers are bad.
Pardon me?
So you say, which one's better? What if all answers are bad?
Yeah, you're expressing a preference. It could well be that both are bad. And I mean, I'm sure there is a technique for dealing with that, which is to say something like, none of these, don't want to do that. But the basic methodology, I should tell you, I have not yet trained with RLHF. I've trained, fine-tuned other models, so I can't tell you exactly, how that stuff is done. But I would imagine that even if you're providing a directional influence, even if they are both bad, you're still providing a signal. As long as it's consistent with the other guys doing it, you will get the system to learn something that is directionally correct. Okay, tons of explosion here. I will quickly point out one simple thing. That is that in this transformer architecture, again, we're going to take as our goal input and producing output. There are three, there's a fork here, right at the very bottom of this tree, which is encoder only, encoder, decoder, and decoder only. Encoder only says, hey, let's take this input and learn a representation of it. Based on that, we do a task. It isn't quite text to text yet. It's text to output, like a classification or something of that kind. This was the first place where really the power of these language models was shown at scale with the BERT model. That no longer is being pursued significantly because people have realized the value of the text-to-text thing that I talked about. So this decoder only says, hey, all we're going to do is get a representation of the input. All our weights are going to be on the output side and the decoder side. The decoder side is learning how to generate coherent text in the way that I talked about. You generate one token at a time using those probabilities, feed that back. This is called auto-regressive construction, and keep doing this. And the encoder-decoder says we're going to do both. Get an encoder representation, decoder. There's still some controversy which one works best. We see a lot of people voting with their feet on this side, but there are some really good results on the encoder-decoder side as well. If you have a bunch of stuff that has complicated semantics, my own rule of thumb is I want to use encoder-decoder architectures. Okay, now we get to the results. This is straight from the GPT paper, and I just whole ton of things. You can go look at the paper yourself. I just point out something amazing here. At IBM Research, I had proposed, clearing the CPA exam back in 2015 as a task to get done. We had no clue how we are going to do it. We started down that path. But now we are at a point where this one system is able to deal with a whole bunch of these tasks significantly better than prior such systems, and often 90th percentile, significantly better than other humans. Just by the way, there are still a bunch of tasks here that it's not able to do well. So we have still a lot of headroom here to go after better results. And in our way of looking at it, we want to break down what GPT, and we're going to give you tons of examples right now. So this is sort of the theory part, how we got to where we are. There are two things that are going on. First, through exposure to a massive amount of text about the real world. And when I say about the real world, I don't really mean that. I mean, it's about the world that humans talk about. It could be the real world. It could also be, stuff in their heads about, fiction and so on and so forth. And importantly, there is no filter here of the sense that says, hey, there's got to be a coherent viewpoint on all this. You will have text describing the same situation, so to speak, from a conservative, a liberal, a clash of viewpoints. And you're leaving it up to this system to figure out how to organize all that, learn the right patterns, so it can come back with some response. I'm saying this just to make sure that you understand we have no a priori reason to believe that this stuff has a personality. It will consistently answer a wide variety of questions with the same integrity or the same real-world groundedness that a human would. We have no reason to believe this. We have to go experiment and see whether it does or not. And the experimentation is, of course, absolutely astonishing, the results that we are getting at this point. So that's the central task here, is to figure out what knowledge it has. And that, of course, immediately ties to the central point of this thing, is about knowledge implementation, knowledge graphs. But this is something that we get out of the box with this approach that we would never have dreamt of getting with a pure, let's go symbolically model our knowledge and represent it in a way that we're going to use formal representations. And I say this with all respect. I used to work, as I said, so much in formal representations, big logical frameworks for programming languages. And all of that is not something that we are working with here. We are going to be doing through a system like this, answering questions, elaborating the incoming text, doing ontology generation without any formal intermediate step where we are explicitly representing things in some symbolic way. None of that is happening. summarization, criticism. You've got some task, you've got some possible output, you give it to the system and ask, please criticize it. Is this right? Is this wrong? And if it is wrong, please try to fix it. You can get this system to do this sort of stuff purely based on the idea that it's going to take some piece of text as input and it's going to produce a piece of text that in some sense follows, given its understanding of all the conversations in the world that has digested, follows from that input. Okay, Nick, I think I am very, very slow here. You want to get started with this or do you want me to do it?
We have a question first.
Since we are approaching this as basically the wisdom of the crowd, and we made some experience with wisdom of the crowd and how good is this? When I hear, okay, let's criticize this, is this right, is this wrong?
Yes.
How is your opinion on that?
Excellent. So here is the great point to make on this, which is this. You don't have to. The hardest part in working with GPT-like systems is figuring out what questions to ask. It's just enormous what you can get this to do. So tell it, you, GPT-4, are an assistant working for me that's going to have a conservative viewpoint. Give it that bias in your input text that you're giving it. And now you should expect to see output coming that is consistent with that. You don't have to rely on it has an inherent notion, personality, view on the world button. You give it that view of the world.
Thank you, Vijay. So let's see, we have 44 minutes left. We have to eat a big elephant here, okay? So, we're a knowledge graph conference over here. The very first thing that you want to do is start creating an ontology. This used to be a task that was, very time consuming and very expensive for many companies. And here's actually an example that Vijay prepared where he basically, he had the ontology and he wanted to see whether we can answer questions. So if you go to the link that I posted in the beginning, and I don't know if anyone can post it from the conference management here, it's called RAI KGC 2023, bit.ly/RAI KGC 2023. You can actually find these examples. And you can see over here how we can give the ontology. Here we're just saying, consider the following ontology, the direct relationship of which are expressed as a CSV file. Assume standard meaning for relationship and ontologies, blah, blah, blah. And then we ask to answer some questions. Please answer questions about this ontology. Explain your reasoning, use the information, okay? And here are the questions we are asking. So it's really interesting how the system responds. Okay, sorry.
Can you just read the questions because it's hard to read the text?
Okay, sorry about that. So please answer the questions about the ontology. If the question cannot be answered based on the ontology, say, I don't know, IDK, and explain. And the question is poison ivy poisonous? Is rin tintin four-legged? Is Humphrey the humpback whale four-legged? Is maize an animal? Is rin tintin a pet? And we don't have to read all of them, but you kind of get an idea. And it starts answering, yes, poison ivy is poisonous. The ontology has the following information, and it keeps going on and on and on. Okay.
So the central point here is that, right, so the first answer is not trying, this is what I said before, it's knowledge the system has, this reasoning capabilities that the system has. We are trying to get it to use such as reasoning capabilities. By saying in the text ahead, here's the knowledge. Here, and the knowledge is given to you as an ontology with these facts. And we haven't even told it how to interpret these things, how to interpret concept of or subclass of, etc. We just gave it stuff that, again, we assume it has seen a lot of this stuff during training, so it has some representation of the meaning of that. We are trying to test if that is what we would expect a system to do. And right there, back there, we got the poison ivy thing. It's just a fact. It got that fact, give us that fact as justification. Tintin, it says I can infer it as four-legged. Why? Because it's an instance of a dog, fact 24, and dogs have the attribute of being four-legged, fact 28. You get the chain of reasoning. Okay. C, was, is Humphrey the humpback whale four-legged or not? It was a whale, whales are mammals are entities, that sort of stuff. It says, I don't know, I cannot establish that. And Mace is my pet cat. Mace is an animal because it's an instance of cat, and a cat is a subclass of animal. It goes through reasoning. Now, I'm not going to tell you that I expect it to correctly answer questions with hundreds of depth in the graph. I don't know. You have to try and see. I would be very surprised if it is able to correctly answer all sorts of questions. We are saying this is probably an assistant to have to help you get off the ground, particularly if you are in a position where you simply want to test your newly developing theory, how that works. Use this sort of a stuff. You will get interesting answers. Pufferfish, not a kind of animal. Duncan is a dog. I don't know.
G is wrong. You should have said, I don't know.
Yes, it should have, and it didn't. You are absolutely right. It should have, it didn't. Yeah. So we go on to the next one. And here we say, now make the closed world assumption. Again, let's not think computer science 1.0 where you got to say what the heck is this. We are going to make the assumption that it has understood what closed world assumption means because of the training set it has seen. That may not be the right thing for it to have understood, given how we understand it. Let's test it out. All we have is empirical experimentation. And here you go. And this is so weird. Again, the challenge is to figure out what are you going to ask this thing. I didn't want to this morning have to go through all of those questions that were answered positively and figure out it's saying, yes, they're still positive. So I said, please give me those answers that would change. And it is able to incorporate an understanding of that requirement in producing only the things that had negative or I don't know answers and revisiting and then telling me blah, blah, under the closed world assumptions. There is no information in the ontology about Rintin being a pet. We can assume that Rintin is not a pet, right? So that is the sort of thing that it's doing with the four-legged stuff. We can, that it is not. Now, it gets repetitive after a while, so that's a bit of a problem.
So the point also here is that, sometimes you're trying to separate from what the language model knows and the things that you want it to know. Okay, and that's, I think, is very important in a lot of commercial applications where you want to make sure that, because there are things that they are different in your ontology from what the rest of the world thinks. So you don't want to make these mistakes, and that's something we're trying to highlight here. So in general, LLM is your collaborator over here. It can really construct a knowledge graph from thin air. And you just saw the example over here where you just have to ask. That's the thing. You treat it as your colleague, as your collaborator, and whenever it makes mistakes, you ask it to revise. Every time you keep asking it, you have to. Every time it keeps producing something, you should never forget to ask, should the ontology be revised? Okay, because you might actually have errors in your system. So let's see another example over here. So this is kind of like Vijay's cup of tea over here. Generated ontology for financial news. It must be rich enough to represent a variety of events of interest in finance, including corporate events, mergers, acquisitions, divestitures, represent information, content of earning reports, blah, blah, blah. So we had a lot of things. And here's kind of like the response, which is pretty amazing. I don't know, Vijay, if you have
Yeah. And here's the other thing. The system has been trained, the system GPT-4, on a lot of structured stuff, on JSON data, on Prolog, on Python. It can emit code as well. Here we are asking it to emit it as a data log schema. It knows enough to follow our instruction. What you're getting is actually a data log representation of an ontology for this domain. I gave it also, it must be rich enough to do all this. I need not have given that. I could just have said, generate an ontology for financial news. And I've done that. And it comes back with something that's pretty boring and vanilla. Again, I'm not saying that this is the perfect ontology to use for all of those things. It's a start. And it's a pretty good start for an agent that I have actually done zero work training to operate on this thing. So what do you see? It says, I've got entities. It says, I have a concept of an entity. This is a fact. Entity has an entity ID, entity type, entity name. Entity types have ID and type name. Financial news has an ID, headline, content, publication data, author. There's an entity relationship between entities and news. That's like this. Corporate events are particular kinds of things because I ask for corporate events. There are earning reports that say, here's the ID for the report. This is our formalization. This is our ontology. What's the entity that this is about? The start of the end date of this period that this earnings is about. Revenue, net income, earnings per share, publication date. Reasonable stuff for a financial professional in this space. And again, I've given it zero information about how to do it other than what you see in the blue. Filing types and so on. Then it's given me examples of this. Company is an entity, central bank is an entity, government, currency, these are entities, events are mergers, acquisitions, divestitures, blah, blah. Filing types are 10K, 10Q. I mentioned these, it got them in the right setting here. I didn't tell it that 10Ks are filed, well, I did say 10K, 10Q filings. And it got that, and it generated some example facts. Acme Corporation, oh, it's an entity. News about it, reports Q3 earnings, it reported blah, blah, and Jane Doe, et cetera, et cetera. So it gave me something, I don't know how, news entity, it actually, so this is an absolutely central thing you have to understand about these systems. They will make stuff up. That's how we're doing this. It's making stuff up. But it's making stuff up based on, hopefully, directions that you gave it. So you're getting something out of value. Here, I believe this is just a completely made up sec.gov URL.
So we have a question actually quickly.
Simple question: is that -- data log schema extra at the end? Was that a part of the prompt?
Yes, it was.
So why?
You can go on the website and look. Actually, I think I made a mistake. There's actually a carriage return, and this goes to the next line. Again, it's just these stupid techniques for prompting the system to do what you want it to do. Here, this should be followed by a data log schema, and it is.
So I don't know, in the interest of time, because we have 33 minutes, I'm just going to go quickly from this example, okay, so we can see more. Here, you can actually ask it to extract facts according to this ontology from the following article. So, in the beginning, we just say create an ontology with a few things. Now we can actually give it a text. And you can go through that, on offline, and you can see how accurate it is in extracting, facts. It's really amazing in other documents as well. And you can actually ask it so you can ask it to revise the ontology based on some new information. Vijay, yes.
Yeah, so if you go back to the previous slide, here's what happens. As I said, these things are hard to control. Think of them as unruly pets or unruly collaborators. They're going to have their own mind. They're going to do certain things. I had said, extract facts according to this ontology from this article. And it more or less did that. It got me a whole bunch of facts that were according to its ontology and correct. And it generated a bunch of facts that were not according to the ontology. Okay? So there is stuff like stock information. There's no mention of that in the ontology. Now, that's why I go to the next thing, if you will. And up there I say, how do these various facts that you got, you produce out of thin air, organic sales growth, segment revenue, again, relevant in this domain, but not in the ontology. So how do you account for all of this? And it says, hey, I can actually represent this in the ontology. It gives you a description that is completely coherent about how to do that. These are financial performance facts. Here is how I would extend the ontology to get this type of logical relationship expressed. And it tells you a whole lot more interesting stuff. And then I say, fine, okay, you did a lot of work. Please give me a single unified ontology which incorporates these changes. And so it emits correctly the previous stuff with this new stuff. We go on, and then I say, okay, now get me all the Coca-Cola news report. Same report. I don't even have to give that news report again. In its conversation history, it knows enough. When I say Coca-Cola news report, to refer to that previous article and extracts all of these things from it. Whole lot of other things it does. It's sometimes too verbose. You've got to tell it to stop talking too much. Okay.
We have a question. Yes, please.
So it's remembering your conversation history, just yours. It's not mixing your conversation history with other conversation histories. Where are the boundaries between the knowledge it gets sort of from the big world and the knowledge it's getting from your conversation?
So the knowledge it gets from the world is during the pre-training. When you are talking to, like, whenever you have a session with ChatGPT, it's basically what you are telling, what you are talking about. So, if there are 3 or 4 users talking to ChatGPT, it's not like going to get mixed and start leaking information from one to the other. No, that's not going to happen. Now, there are some concerns whether OpenAI is using these conversations to keep refining the system, but they're being very, very careful about that. They promise that they're only going to use, let's say, 200 conversations per no, even less than 200, something small from every user, and you always have the option to opt out. You can say, I don't want to use my conversation. And I think they also are very worried about that, and I think they're switching to other modes right now.
It's very simple. If you're concerned about this, go to the paid subscription, and none of the stuff in your paid subscription will be mined by them for future training of the system. The other important point to make is, as Nick was saying, these separate conversations are all separate. The system is learning nothing in the context of this conversation. Its set of weights that existed before you started the conversation and after you terminate it are exactly the same. It's not learned anything. But it has this capability within the way it's constructed and built all its weights up, it can carry some memory about your past interaction in the context of this conversation. It's a very subtle point, but as soon as you stop, that's gone. It doesn't, its weights did not change.
Can I ask a follow-up question?
Yes, yes.
So if OpenAI is keeping some subset of conversations as part of the continuous learning of the system, can a bad actor intentionally feed it misleading conversations and misleading results?
2 + 5.
Absolutely certain that's happening. That's what they did on the Tay chat or whatever it was from Microsoft. Within a couple of days, they had to take it out because people are feeding it all sorts of bad stuff.
Yeah, but typically when, they're very careful when they're retraining, they do a very careful process of picking conversation. This is called data poisoning, that for many years in security, people thought that it's like a fictional research, a fictional scenario, and it's coming up now. People never thought that it was going to be.
There's a question.
Yes, sorry.
You and I both know a lot of the big banks have invested a lot of energy in building logical data models, inside out ontologies. How do you see, like, for example, Legend? How does Legend?
Rest of the talk.
Yeah.
It will come up. You can deal with this.
So
Going there, but
quickly over here, that's also another interesting scenario where somebody says, I'm a financial analyst, and we have the war in Ukraine. Can you predict financial scenarios? You're asking about the exchange rates and the GDP growth. It's also very interesting, watching that.
Out of no other input than to say, I care about these set of macroeconomic factors. You're looking for it to make coherent scenario descriptions which correctly argue if this thing goes up, that other thing is going to go up and so on. It produced 3 scenarios, and each is internally consistent in the way that you talked about. It's all on the website. You can run it yourself and see that, in fact, this is, again, interesting to start with, not the final word.
What is very interesting here is that the model was trained with data up to 2021, so there's no way that it had read a blog or a financial analyst. Okay, so it's completely original here. So now the next step is like, how are you going to work with structured data? So basically, I believe a lot of you are already vested in KG, so you have KGs developed. And I mean, what do you do now that you have a language model? You don't want to throw that away. Okay, so first of all, this is, you might have seen that with SQL, but it's a really out-of-the-box functionality where you can ask it to generate a data log code over here. So you give an example about what is mommy, what's the definition of parent. And because GPT-4 has seen a lot of data log, Python, JSON, Prolog code, it can very easily solve that problem. And it does it really well. Now, I want to make a point. 3.5 is not really that great when it generates code. That's why we insisted about using 4. So there's a big leap, a big gap, working with 3.5 and 4 when it comes to generating code. Now, this is a very interesting example, which we spent a lot of time with Vijay, thinking about, okay, you ask some questions, trivia questions. What if you ask a really complicated question, which is, I'm just going to summarize over here. I'm in New York. I'm going to be here from 9 to 5. Like, you're a tourist. I want to go to 3 art museums, 2 history landmarks. Vijay ran that with Indian food. I ran it with Greek food. It works the same. Okay. And I don't want to walk more than, 5 miles. Now, if you ask it just this question to do the reasoning, it's going to return something that looks really realistic. But when you check it out, it's going to be wrong. It will probably get right the art landmarks in New York and the historical landmarks, but it will definitely mess up the distance computation. So you actually end up walking a lot of miles, not what you asked. Now, we actually helped it by saying that, look, when you solve this problem, don't try to calculate your distance on your own. Use the Google Maps API key, and also try to do it in this order, okay? So imagine like you are a scientist and we are instructing someone to write the code. This is what you would do. And it did it's almost correct, okay, but not quite.
Also, if you go back, we actually said it something like this. Use the integer programming library pulp to solve this problem. It's not just go do something. It's actually, you will need, we didn't say that you've got to, oh, we did say here, it should use pulp to solve a traveling salesman problem. Now, I don't remember the pulp APIs, okay? And please give me the program. I didn't say stupid program, but please give me the program. Make sure it is using pulp APIs correctly. And look at that. You got, I think somewhere we said Python program.
Yes, we did say that. So that went through several iterations. Even in the beginning, it could actually realize that it was a TSP program. I was getting the code wrong because it's not exactly traveling salesman. It has more constraints. Now,
Nick, did you run that program?
we actually ran this one. I think this one actually runs, the one that is generating. So here we became a little bit more detailed, especially how you are going to, formulate this integer optimization program. Now, you might be thinking, okay, isn't that too much of work? Yes and no. It is too much of work for us to do it now, but remember, we are being now some very expensive annotators. When ChatGPT came, there were some people who were, high school graduate maybe, that they were teaching it doing simple stuff. But imagine now 100 VJs and, and 100 people like you over here working for a few months, formulating optimization problems and teaching the system how to do it. It will soon be able to do that first, do that well. Now, let's go to another problem. This is part of the ontology from a large telco. When someone wants to run a semantic search query, okay, so you're asking, find the cell tower who receives most of the calls from customers who live in a specific address. Okay, and this is your ontology. Now, 3.5, you can try working with it, but it's not gonna give you a query which is wrong. But ChatGPT 4 actually produces the produces the right query, and that's in SQL. Okay, yeah, that's in SQL. And all I had to do is just basically take the ontology and write it in that form. Okay, because for now it doesn't understand pictures, but soon it will understand pictures as well. So that's kind of like an approach. You've heard Microsoft, and everybody's trying to kind of like move toward this, paradigm. The problem is that, if you go to the real ontology of the telco, it's not really that simple. It's much bigger, and the queries can be much more complicated. So I know that these kind of like toy examples, sound impressive, but as we saw in the previous example with a very difficult question about navigating in New York, the model is not gonna do it, okay? So there's a different approach where instead of asking, okay, to formulate the query, here are 3 different samples. I'm asking, can you find, entities and relations in my ontology that they're going to be useful for me to answer that query? Because when I say customers, in your database, there might be users, there might be subscribers, there might be something else. So in that particular case, it gave me some entities and relations that they're actually all of them exist in my ontology. And then we don't have to throw away all the work we've done with our knowledge graphs, because the knowledge graph is very accurate, it's very accurate. So basically all you need to do is find out which entities and relations you have to visit and start traversing your knowledge graph. And by traversing the knowledge graph, you can actually produce an accurate query that is going to run. And it's verifiable, that it works. Because your ontology has integrity constraints, has a lot of safeguards for you so that you can actually run it. So I think that's a great example about how you can use language models with a big symbolic, know-how that you have in order to, produce useful results. And now we're moving to the next session, which is, I like the title, a language model tradecraft. And I want to start with the very first thing. 2 years ago, they asked Percy Liang, who is a professor at Stanford, what does he think about prompting? And it was another conference, was the AKBC, Automatic Construction of Knowledge Bases. And he said, prompts are going to be dead pretty soon. And people were actually laughing. It turns out that he was right from a different perspective. If you remember in GPT-3, we had all these people called prompt engineers that they were trying to, it was very fragile the way that you were phrasing things. Whether you put a carriage return, whether you put a space, capitalize, say differently. And it turns out that the big jump from GPT-3 to 3.5 was moving from prompts to instructions. And you can see that even 3.5 is quite robust to instructions. So that whole idea of prompting kind of like, we still call it a prompt, but in reality, as Vijay alluded pretty extensively, these are all instructions. They are not prompts. You just have to be, and something else that people find very difficult is that you have to actually treat ChatGPT as your colleague, like the way you speak to it. It's not this mechanical language that you used to use for computers. Now, there's also the notion of like fine-tuning. Vijay spoke a little bit about that. You can always fine-tune a model. You can fine-tune ChatGPT. You can fine-tune a T5 or GPT-3. And they work well for a number of tasks. Well, the main drawback is that it's very expensive to generate a data set. But there is actually a new technique, and a lot of people do that, where you can use a more expensive model in order to distill knowledge. So you can basically generate your training data set. Now, fine-tuning hasn't gotten a lot of attention just because, let's use prompting or instructions, tend to work really well. So this is from the paper from Izhen Choi, where she actually, we don't have time to go through that, shows you how you can extract symbolic knowledge out of an LLM. And that actually might be pretty useful because a lot of companies still operate with knowledge graphs, and it might be a good idea to keep working on that if you can extract the knowledge.
So just to make a big point on this thing, the group started with GPT-3, so the stuff inside it, and extracted from it knowledge-based facts in English. This was common sense knowledge. So this is symbolic knowledge distillation. This kind of thing, there's a lot of other papers in this space. This kind of thing is getting increasing attention. Go from a machine to essentially a data set. It's not curated by humans, it's machine produced. Then use that to train a smaller model.
Okay, so the other thing that you might have heard a lot now, it came with deep learning, is the word embeddings. If you're not familiar with it, embedding is actually the cornerstone of deep learning, in my opinion. We actually have a presentation posted on our side of how we came and why embeddings are so successful. But the main idea is that you're taking text and you're converting into a big vector. How big? Right now, actually, OpenAI is giving you 1,536 floats. And the premise is that if you have like two things over here, the kids enjoyed splashing water, you take a vector representation. My children love water parks, embedding number 2. We know that they're semantically similar, so you kind of expect that the distance between them is going to be small. That's kind of like the whole premise of embeddings. And a new category of databases was born with embeddings. It's called vector databases. And the idea is pretty short. Where you do vector search, you just have your string associated with a vector, and then you have a question. You take this question, you convert it to another vector, and you just do nearest neighbor in that database. You do a lookup in this continuous domain. I think most of you are probably familiar with that. There's a lot of players right now in that domain, a lot of open source and commercial products. You might have heard like, Pinecone just raised 100 million over there. It's a very rapidly increasing category. And actually, this is a great article on Medium if you want to understand more about what you should choose if you are looking for a vector database. And you can think about the vector database as an external memory to the language model. So Let's take a simple example. Okay, so you are a company, you have 1 million documents, and you somehow want to use them for your language model. So you take every document, you split it into passages, something about 100, 300 tokens, maybe no more than that, and you embed it. You use OpenAI, or any of your favorite embedder, and you store, the passage along with the embedding. So the embedding is the key, the passage is the value. Now, when somebody goes and asks a question to the language model, like here, is the debt of GE higher than GM? List documents that would be relevant for you to answer this question. If you embed that question and you go back to the vector database and find passages that they are semantically similar, you retrieve them. And it's going to retrieve a lot of passages that they're not really relevant, but it's going to retrieve a lot of them that they are very important to ask that question. Now, once you throw them into the large language model, where we've seen how powerful it is in terms of answering questions, then it can actually start making, providing you with good answers. And that might not really happen in one pass. You might realize that something is missing, so you have to keep asking, are you sure? Is there anything else? Tell me another question that can help you fulfill that goal. We're going to see that later. Vijay is going to talk about multi-hop reasoning, where you keep asking and retrieving. It basically does the same job that you would do. If I was asking you that question, you would just go to a cabinet trying to look for files from SEC, and then trying to locate the passages, and then going back and forth and find out what is missing. Okay, so, and I just described this, this process over here. So I want to make sure that we get to some other fun stuff. And here's the multi-hop reasoning. Vijay, I don't know if you have any comment on that.
Just quickly, I think you made a very important point that I want to make sure people don't, gloss over, and that is this system can actually take more information that is necessary for answering the problem at hand, and it knows to ignore that. So it is okay. And so all the critical factor here is the size of the input that it can take in one go. With GPT-4, we are working with 4K tokens. That's a lot. That's something like, let's say, 2,000 words, 3,000 words, actually. There is a 32K model, which has 40 pages of input. So you can throw in a huge amount of information specific to your problem and get it to solve, again, not the world knowledge that it has, using those linguistic capabilities. So it's really getting to be in a very interesting position from a use point of view.
Please, you have a question?
Yeah, I mean, I've been trying to play around with these with tools like this, and I'm blowing my OpenAI API bill up a lot. So, do you guys have any best practices for how to, use these things so it's not as expensive as it may need to be?
So it's a good practice not to. So, for example, even if you have 40 pages, this thing is charging you per 1,000 tokens, per token, basically. Okay, so one of the reasons why people, we're going to talk about that, these external vector databases, is because, it reduces the cost by a lot. So instead of throwing the whole 40 pages SEC, document, you can vectorize it first and try to find out, which one is the most relevant. So, you go down from 40 pages maybe to 2 pages that it's going to look for.
Let me just say a simple point, and this is also extremely powerful. Again, the challenge here is for us to figure out how to use the system. It's a really odd way of putting it. So here, this is the so-called hot pot reasoning problem, multi-hop reasoning. You've got a question. To answer the question, you actually need to combine information from multiple different passages. How do you do that? As Nick said, we're going to do an iterative version. So you get the initial question, you ask related passages, it gets 10. But now, they will not contain the information adequate to answer. So you change your prompt. You don't ask it to answer the question, just answer the question. You tell it, please answer the question if you can. If you cannot answer the question, return a question which, if answered, would enable the original question to be answered. This is abduction from logic a long time ago, okay? Works beautifully. So in other words, you've got to start thinking how to use these linguistic capabilities to get it, it's a generative thing, to get it to do more of the problem by producing subplans, by producing other parts that would help it. It doesn't know enough to solve it in one go for you. You've kind of got to work with it to get it through multiple steps. Please.
Yeah, so this basically summarizes what Vijay described over here, but gave it a new name called language machine. So, sorry, you got a question?
Thank you. I have a question about you. You say that you give an example and ask the ChatGPT to generate an ontology for you, specifically on financial method. And you have to change the prompt until it generates a good ontology. Do you think that maybe an expert will do it quicker than ask the ChatGPT?
No, it's a good question. It depends on how expert someone is, and depends on how many experts you can have, because this is a fairly cheap expert, in a sense. So we've actually seen cases where it does it faster than we do, and there are some other cases where it needs more work. But in general, I want to say that it's pretty good at getting it. Yes, 3.5 is actually super fast generating. The 4 is still slow in deployment. Okay, so
yeah, but the time that it takes you to get to the right prompt, it doesn't equal to the time it will take you to create an ontology by yourself.
The prompts are not really that difficult. I mean, if you saw what Vijay asked before, it wasn't. It's really literally talking to a human. Like if I ask you something, give me an answer that I'm not happy, then I know what's the next thing that I need to ask you. Says, no, I didn't mean this, I meant that. And please don't use these words, use some other words. So I feel like it takes some time. I mean, I think the problem is that people expect it to be very hard, but in reality, when you start using it, I mean, we had a lot of experience with very senior programmers that I couldn't believe. Like they started with the most difficult thing, they realized that, oh, it's just like a conversation in the end. So, you'll be surprised. A lot of very experienced C++, Python programmers, advanced like Tiger teams, they are actually surprised about how quickly it can generate the code, and it doesn't really need that much of an expertise. So it's more about getting comfortable with it and not really finding tricks. This is not like the SEO examples where you had people that they had to hack the Google index and figure out how to bring you up. It's a much simpler process,
Yeah, and that's it basically. I'm a programming models guy, right? We did logic, we did Java, X10, all of that stuff. This is a new programming model. We're talking with text to the system. You got to put aside your previous experience with this stuff and now really talk to it as if it is a collaborator and get things. It's not that difficult. And of course, your mileage will vary, so just try it and see. You'll get an answer about whether it's cheaper doing that than getting an expert. Last thing I will say on this topic, same program will work as, quote, your expert on 10,000 completely different topics. There's a whole new thing emerging here, which is getting the ability to create, interesting ontologies in many different areas.
I'd just like to give you an example. When we were preparing this presentation with Vijay about creating ontologies, I said, but Vijay, we have to give them an example that it doesn't understand the ontology, and we have to give them, the documents. So we tried very hard, and I said, well, what do you mean? I said, well, ask it to give you an ontology about rocket engines. What does it know about rocket engines? And then it actually was able to generate some pretty detailed ontology about rocket engines. So yes, there might be some areas that it doesn't know. We still haven't, haven't found one. I think Vijay, is that your part?
All right, thank you. Okay, we are talking 6 minutes, so
we're gonna be late.
Yeah, so I'm actually just going to skip over this. So here, I mean, we've spent a lot of time with this stuff. I've been working on this since GPT-3 around 3 years ago or so. And so there's a whole view on where we see enterprise software going, particularly centered around knowledge extraction and so on. Unfortunately, we don't have time to do this, so I'm just going to skip over it. Lots of interesting stuff. We can talk to you later about it, but let's get to the elephant.
Okay, so the elephant in the room is basically you're all coming from companies, you have your data, and the question is your CEO or your CIO comes to you and says, okay, so what do we need to do? Should we use the symbol of Pinecone, a vector database plus ChatGPT, or should we use humans to curate a knowledge graph? So what's the answer over here? And we start saying, okay, let's think about what are the things that we claim as knowledge graph enthusiasts that we can do better. And this is an example from a relational AI blog post highlighting that working with things and not strings, it's much more powerful. And we give the example of Turkey, who recently changed its name as a country to Turkey, where it's a different spelling. And if you were using strings and you had 500 databases, you had to go and change that string versus having an entity. Okay, and you can read the blog post how you can manage this abstraction. And then we said, well, let's go to GPT-4 and ask, what was the population of Turkey in 1990? Okay, you expect that. And then we ask, what was the population of Turkey in 1990, which this country didn't have that name then. So it responded perfectly naturally over there. So with that, maybe because it knows, these embedded systems, these systems that use embeddings, they're pretty good with, with synonyms. Remember word2vec. And then say, okay, let's try to trick it. And I ask, who was the president of, let's ask with this one, of Zimbabwe in 1970? It was intentional because Zimbabwe didn't exist as a country. It had a different name in 1970. So it said, in 1970, Zimbabwe was known as Rhodesia, and it was not yet an independent country, blah, blah, blah. The president was this guy. And if you ask it about Rhodesia, it gives you more or less the same answer. So this is not just synonyms over here. It was able to recover the timeline and basically give you an answer that was correct. Okay, so it does have this abstraction of the country, okay, which is somewhere in South Africa, and it has this history. Sorry.
It seems to have a different date when it became Zimbabwe.
Sorry?
It seems to have a different date. It said 79 in the first answer and 80 in the second.
In the first, sorry. 1970. Well, the truth is, to be honest, it became Zimbabwe. It says 79 versus 80. The truth is that because I searched that, it didn't become like within a year. So there's different. Yeah. Again, as a some of these questions, even in real life, they don't really have a good definition. That you'll see that in another one which I discovered. And then we, since we're in finance, we said, okay, who was the CEO of Truist in 2015? For those of you who don't know, Truist is, as a company, didn't exist. It's a merger of two companies, SunTrust and BB&T, which actually happened in 2019. And in fact, that might be wrong because, with mergers, they start and then they finish at a different day. So I'm pretty sure that was a little bit later than 2019. But anyway, it did get that. It says, well, there wasn't the CEO of Truist in 2015. But, there were two companies, and those were the CEOs. And, as you said, sometimes things can go wrong. And I think that's a famous example. You might have seen it when you ask it, what was the first animated movie? It tells you about the Snow White, which is not really true. And then you say, are you sure? Can you about your answer? Is this the correct answer? And then it says, it's El Apostol. And then the truth is, sorry, again, this is actually the 3.5, what we have over there. Sorry.
So it got it wrong as well the second time.
Yeah, it was. I think this is, I forgot to put that. This is 4 and this is 3.5. Now, if you actually search the web, some sites claim that it is the El Apostol, but if you ask Google, it has a different opinion, because right now this is borderline. Like, some people consider that this is not really an animated movie. This is something less than that. But anyway, the truth is that it did hallucinate over here. It did give you an answer that wasn't correct.
This is sort of very quickly on this. This is a point here. Why would you have to say this? This is like, zero information you're supplying to the system, but it was able to use that trigger to change its answer. And that's the point. There's a ton of stuff that's implicit in the system that if I were to use the knowledge terminology, it doesn't know about this. It doesn't know about the stuff that it knows or the stuff that it doesn't know. And through your interaction today, we've advanced from the 3.0 days. Through your interaction, you can help it to know more about itself. Unfortunately, because this is doesn't learn anything outside the context of your conversation, it's not going to change its behavior when you go away and someone else comes in. That's a whole different game that you can actually learn from this stuff, put things out in a knowledge graph, use that as a pre-processed or a cached version of things, and then get better results with a combination of a caching knowledge graph and this backend system. Many more interesting architectures to go to.
So let's kind of like summarize what are the pros and cons. So converting text to KG, when you do something like that, the facts that you're producing are reliable because they are reviewed by humans. The other thing we haven't talked about, actually you talked about, is the cost. A KG is much, much cheaper than a large language model. And something we didn't, I want to give credit. Okay, thank you. We stopped the beeping. It comes from there. Okay, they stopped it. We're going to be a few minutes late. It's fine. Isa will keep the food warm and the drinks cold. Okay. So, one of the most remarkable things about OpenAI is not the performance of the model, that they actually are able to scale, at millions of users. And the other thing is that the heavy lifting is done offline. Okay, so when you're building the KG, you have people, so that's why when you are serving it, it's much faster to serve that. And the truth is that the KGs have very powerful, recursive and reasoning capabilities. Now, the biggest problem, elephant in the room, is that you need to know a priori what entities in relation to extract. Okay, so if, all of a sudden your system needs to answer different type of questions, you have to go back and start re-extracting information from your database, and that is really difficult. Now, let's see the pros and cons about working directly with text and language models. So basically, language models and a vector database, everything embedding. No, the nice thing is that documents can be added and removed dynamically. So if you don't want something to be in your knowledge base, you just take the document off. We saw that there are still some very powerful reasoning capabilities in a different way. And of course, the biggest advantage over here is that, natural language for querying, it's much easier than, querying a knowledge graph, if this is something that you have to expose to the users. And it's easy to do multi-hop querying. Now, LLMs can have very high latency. Multiple LLM calls, as you mentioned, might be required, and this, throws the cost very high. You need an extra vector database. They're not super expensive, but that's an extra component. And embedding the documents is also not a cheap. It does have a cost. Okay, it's not negligible. It's not super high, but it's not negligible. And that's kind of like something that we investigate a lot, and there's a lot of research on that, whether it actually makes sense to run the language model or have the language model as being part of the query plan into your knowledge graph. So you can always think about having a relation or a predicate or a table, like a virtual table, that's your language model. And there's a lot of question, how do you do your whole query planning on that? So Vijay, where do we go next?
All right, thank you so much. So I'm sorry we ran a little bit over time, so I'll cut this short. Back in 2015, I had responsibility for trying to produce a sketch for IBM Research's AI research view of where we are going to go. And back then, this notion that, look, most of the techniques that were actually valuable at that point are in the so-called perception layer inside. There are a ton of stuff to do on the reasoning. And then, of course, in what I was calling intelligence at that point, things like developing mathematics, thinking strategically, using emotion, programming. Well, we are seeing expanding out some portions of this. All the debating stuff that IBM Debater did at that time, a lot of the stuff I can get out of GPT. I don't have time to show you those examples, but I've given it complicated legal judgments, text, and asked it to summarize the arguments beautifully. Not only that, but ask it to tell me how I would appeal this decision at the next higher court. What argument should I make? There's stuff to do here, guys. Okay, so we are getting to that sort of stuff. Reasoning ethically, big thing, not yet dealt with. Supporting people, managing people, entrepreneurial reasoning, so much stuff to do. So very exciting time. I hope you have seen tons of things that the system is now capable of. And by the way, we just picked GPT-4 because it was easy for us. It's out there. We can run queries, just pay some money to OpenAI and you get all of these results. There are lots of other systems like this out there. Please go take a look, and I hope you enjoy this presentation.
So if you want to keep an ask, or maybe we can take the questions in the social, actually. Yeah. We have the slides actually.
Oh, awesome.
Yeah, so if you go to that document, if you go to this slide, there's a slide, but if this will take you to the document and that has the link.
So the bottom line is it has to be integrated. It's such a big